Welcome, everybody, to the very first paper session of this conference, which is on distances. And the first talk is by Guillaume Coiffier on, as you can see, one Lipschitz neural distance fields. Please.
Thank you very much for the introduction. Good morning, everyone. It's a pleasure to be here today. So the question I want to answer with this talk is how to compute a good implicit representation of some geometrical object. So implicit representation of geometry is an interesting paradigm where, unlike usual representation involving point clouds, meshes, or voxels, here we only work with functions over space, and we define geometrical objects as some level sets of those functions. So for instance, here, this bean-shaped object omega is defined as the sets of space for which the function is negative. And of course, if you want to represent some object, there are infinitely many functions that could have the good level set. And among those functions, one that is of particular interest is the sign distance function of your object. So as the name suggests, is simply the sign distance function for a point x is simply the distance of x to the boundary of your object, counted positively if your point is outside and negatively if your point is inside. And what makes this function interesting, well, among other reasons, is that it satisfies a particular partial differential equation called the aconal equation, which states that its gradient has unit norm everywhere, plus some boundary conditions on the boundary of your shape. So maybe that sounds very theoretical and abstract, but as a matter of fact, if you have access to an implicit representation of an object, and especially a sign distance function, you can already perform a lot of applications in geometry processing and computer graphics on your object, so including constructive solid geometry, rendering using sphere tracing algorithms, extracting a mesh, or even perform some numerical simulation using Monte Carlo methods. So this is having a sign distance function of an object already, with this you already know a lot about your geometry. The problem is that computing a sign distance function in general is very hard. So if your object is simple enough, you may be able to compute the distance as a closed form and in a few lines of code, but this becomes quickly intractable for more complex objects. So this is why, in the last few years, people have turned to deep learning to try and approximate sign distance functions using neural networks. And those so-called neural distance fields is what I want to talk about today. So what is a neural distance field? Well, the idea is very simple. It is to define some neural network f theta with parameter theta and define some data set on the object you want to represent. So here, this hammer silhouette. So you sample points in a domain around your targeted geometry, and for each point, you suppose that you have access, you have computed in advance the sign distance function that you want, s of xi. And using this dataset, you can minimize some losses on your neural network. The main losses that we find in the literature are the following. So some kind of fitting loss that encourages the network to match the output of the sign distance function. And then some regularization losses on the gradient of your network. One that tries to align the gradient with normal directions, especially on the boundary of your object. And the infamous aconal loss, which encourages the gradient to have unit norm everywhere to satisfy the aconal equation. But this approach is my opinion. Well, first, it works quite well in practice, but it has two critical limitations that we want to address. The first one being that we are doing deep learning, so there is no guarantee whatsoever that it will converge to the global minimum of our losses, which means that in practice, you do not have an exact representation of the sign distance function, but something that approximates it. And if you're doing an approximation, you may overestimate or underestimate your distance, because the norm of your gradient may be greater than 1 or smaller than 1 in some areas of space. And if the norm of the gradient is greater than 1, if you overestimate the distance, and you want to perform some geometrical queries on your objects, for instance here, a projection onto some level set, then you are not guaranteed to either converge or you converge to the correct result. So that's a problem. And in practice, if you want the query to be guaranteed to have the correct result, you want an underestimation of the true distance. That is to say, you want the gradient of your function to be smaller than 1, which translates to having a function that is 1 Lipschitz. And in this case, if you underestimate the distance, you will never overshoot the surface, and so iterating the projection operation, you will always converge to the correct result. So this is a problem of robustness of neural distance field. And the other problem is a bit more tricky, because as I mentioned, if you want to learn a distance field, you first need to have a data set of points with associated distances. That is to say, you need to know the distance to learn the distance, which is a bit redundant. And this greatly reduces the potential applications of such methods. Because in practice, you may not have access to the sign distance function, or it may be not possible to compute it. So if, for instance, you consider inputs like corrupted point clouds or noisy data, then you cannot generate a clean data set to learn the sign distance function. So these are the two problems that we want to address with our work on the 1 Lipschitz neural distance field. So the idea is to first use, let's look at robustness first. The idea is to use a 1 Lipschitz neural network. So what is a 1 Lipschitz neural network? It's well, a family of works that has been studied for about 6 years now. And this all starts from the following observation. That is, if you define a neural network, often made of layers, what you do in the end is that you define some functional space that is the set of all functions that can be represented by your architecture when the parameters change value. So instead of relying on losses to try and impose the property that you want on the network, what if you could define this functional space as a subset of all the functions that have the property that you want? In our case, what if you can define this subset, this functional space, as a subset of all the possible 1 Lipschitz functions? And it turns out that we can do that, and there are several methods to do so, to parameterize a neural network to only represent 1 Lipschitz functions. Since Lipschitz functions are stable by composition, it's sufficient to only represent one layer of the network. And we propose to use this, this formula for the layer, which was proposed by Arjo and colleagues, which is perhaps the most recent one and maybe the most efficient one, which is a modification of a classical layer. So usually in a neural network, what you get is x as an input, and this output, sigma of w times x plus b. So w is a weight matrix made of parameters, and b is a bias vector, and sigma the nonlinear activation functions. And what the authors propose is to modify this layer to add here a diagonal matrix parameterized by some additional parameters q, which are the same, which is a vector of the same size as b, and add a bit more computation. And it turns out that if you do things like this, this layer is indeed 1 Lipschitz by construction, which means that we can parameterize 1 Lipschitz function. So if we go back to the problem of learning a neural distance field, and if you use 1 Lipschitz neural network instead of a classical architecture, what we have is something that by construction will never overestimate the true distance. So here the gradient of our neural distance field is close to 1 almost everywhere, but always smaller than 1. And especially the areas where the gradient norm is small correspond to areas where the sign distance function, the SDF's gradient, was discontinuous in the first place, that is to say, points on the skeleton. So this is interesting, and we'll talk about this in the results. But the main key point to take away here is that even if you train with regularization, like the Eikonal loss, you won't be able to enforce this 1 Lipschitz property. So we have to work directly on the architecture. So that's the first problem we talked about, the problem of robustness. But now, since we have a 1 Lipschitz neural network, we can take advantage of this property and try to get rid of the ground truth distance in the training procedure. And it turns out that we can. In fact, we are able to learn a sign distance function directly only from some kind of occupancy labels. Okay, so suppose that on our shape omega that you want to learn the SDF, we can determine some function y that is basically the sign of the sign distance function. So -1 if x is inside omega, and +1 if x isn't. And from this data, we can define a new loss, well, first proposed by Serrurier and colleagues, which is a binary classification loss called the Hinge-Kantorowicz-Rubinstein, or HKR loss. So this monster is made of two terms. The first one here is simply -y f of x. What it means is when you try to minimize the HKR, minimizing this first term means that you encourage the network to output the greatest value possible for points outside of your shape, and the greatest value negatively for points inside. So in other words, it tries to pull apart values that are outside from values that are inside. And since your function is one Lipschitz, you will hit some limit on the increasing of the function, and this limit will be the sign distance function, as a matter of fact. If you are familiar with optimal transform, you may have recognized in this term the dual formulation of the Wasserstein distance, which is expressed as the maximum of all possible one Lipschitz function of f of inside minus f of outside. This is basically what's going on here, and this is a nice connection. But this term alone is not enough, so what was proposed in the work of Serrurier and colleagues is to add another term, which is a hinge loss, which in practice simply penalizes points which are misclassified by the network. So this loss is non-zero for points where the sign of f and the sign of y are not the same, up to some margin m, which is here for stability of the training. And what's interesting is that this is a binary classification problem that's already been studied and published, but we can show that actually the minimum of this loss over all possible one Lipschitz function is the sign distance function of the object you want to, the object you consider, up to some error which is of order of the parameter m. Which means that only using occupancy labels y, we are able, by minimizing this loss, to learn the sign distance function, to approximate it. So all there is to do now is to well, compute the function y. That is to say, define whether this boils down to knowing whether a given point is inside or outside the shape, a problem that has been well studied in deep learning, in geometry processing. And since we already have a lot of available solutions, we decided to use the generalized Winding number to determine whether a given point is inside or outside. So this Winding number, in a nutshell, because I won't go into details, is if you have it's basically an integral of solid angle from your points to all surface elements of the shape you consider. And if you have a closed manifold that is non-self-intersecting some clean data, this will output a binary value, either 0 if you're outside the shape and 1 if you're inside. So you directly have your binary classification. And from this label, this occupancy data, you can compute the sign distance function using the HKR loss. And this is a Winding number, the correct Winding number, but it can be generalized to not so clean data, especially point clouds and triangle soups. And in this case, what you get as a result is a continuous value between 0 and 1. But through careful thresholding, you are still able to determine the inside from the outside in this case, and still able to recover a sign distance function that is very close to the first one. So that's basically it. So the method we propose is actually quite simple. As an input, you can take anything you want, basically, any point cloud or triangle soup or whatever you want, as long as you are able to determine through the Winding number whether a given point lies inside or outside your shape. Given this input, you can sample points in a domain around your geometry, uniformly, for instance. And you can use the Y number or any criterion you like to determine points that are inside and points that are outside. So you compute this Y in -1 or 1. And given this input data, you minimize the HKR loss over this dataset for some one-Lipschitz architecture. And what you get is a very good approximation of the sign distance function of your object. So that's basically all there is to it. So let's look at some results. So first of all, since we are some comparison with other approaches to show that we are quite comparable in terms of reconstruction precision, but if we look at the norm of the gradient, we are the only one to guarantee that we will never exceed 1 and overshoot the true distance function. Which means that in practice, we can perform direct geometrical queries on our neural network without needing range analysis or Lipschitz constant estimation or all the machinery that is usually needed to correct the defect of such structures. So if you want to perform, let's say, ray matching, you can just take your network, feed it out of the box to some ray matching software, and recover the image. And the same goes for sampling any level set. You can project on the level set by iterating, and you are guaranteed to converge and have the correct result. Another application that is interesting and unexpected at first was the sampling of the skeleton, because as I said, the points where the gradient of our network is way smaller than 1 in norm are the points where the sign distance function was at a discontinuous gradient. And so by sampling and rejecting those points, we can actually perform a sample of the skeleton of the shape, which is nice. And since we didn't need the true distance to learn the neural SDF, we are able to learn the distance function from very bad inputs. For instance, here, point clouds with holes, point clouds where we simulated the noise and the acquisition of a LiDAR, very noisy point clouds or very sparse ones. In all of those difficult cases, we are still able to recover the correct geometry of the sign distance function of the zero level set. Basically, as long as your inside-outside criterion is correct, you will get a correct result. So, yes, and in order to, a last thing before I conclude, I've talked about signed distance function, but this method also applies to unsigned distance fields, for instance, associated to curves and open surfaces. And this is even more simple. You just have to take the occupancy labels to be -1 on your shape and not in your shape, and +1 everywhere else, and then you can train, and you get a distance field. And what's interesting here is that the margin parameter we added in the hinge loss actually acts as some kind of thickness of reconstruction. So if you have a large margin parameters, training will be easy, but you have some imprecision. But small margin parameters, or m going to 0, will lead to more precise results, but training of the network will be more challenging. And so this works in 2D. This also works in 3D, here with different level sets of the same object. And we have here a curve and an open surface with holes. And so this also applies. This is exactly the same method, and we are basically able to learn a distance field from anything. So that's basically all there is to it. Here is a link to our code, even though it's not very clean at the moment. I will clean it if I have the time. So I will stop here and be happy to answer all your questions. Thank you.
We have time for some questions. Yes, go ahead. Do we have the microphone? It's coming.
This on? Great. Yeah, so I noticed in the formulation of the HKR loss that you're using,
Yes.
the labels, the Ys, it doesn't seem like there's anything in that loss that requires those to be binary labels. And the generalized winding number is giving you these continuous values that you then decide to threshold. Is there a reason why you didn't just use the continuous values in that loss, or, yeah?
That's a good question. If I recall correctly, at some point I used the smooth labels to learn. I don't think it changes a lot in the results. So what it would mean is that you have less loss in areas where you are unsure of whether the point is inside or outside. So, but I didn't see very much of a difference. So, but that's a good question, yeah.
Thanks.
Beautiful work.
Thank you.
Really like the approach to fitting this function to this one Lipschitz function. A question about your use of generalized winding numbers. So we've found that when surfaces have large holes, not just small, little noisy missing data, generalized winding number does a really, really poor job of providing a surface completion for two reasons. One is there's no clarity on what parameter value you should use to contour the function. So for different examples, you need to use different ISO level sets. And the other one is that both generalized winding numbers and Poisson reconstruction fill the data with a harmonic prior, right? So you have this harmonic function, so if you have a big, large missing piece, it fills it in with something that looks like a minimal surface. And so I guess the question is, did you run into this in your examples? Is it simply that your examples don't have these large missing patches? And is there something you can do about this sort of poor completion that you get from generalized winding number?
Actually, we had some examples with large holes. So not this one here. The holes were quite small, but this input, for instance. Sorry, I don't have the image in the slides, but here we are able to reconstruct the holes. And what we do is we increase the threshold on the winding number. So we only take points that are very close to 0 and very close to 1. So there is a big area where there is no point. But since the network learns a continuous function from negative to positive, it will cut somewhere. So we'll have the same kind of bias that is close to a minimal surface, yes.
I see. So your method is actually adding an additional prior on how to complete the surface beyond just what's given by generalized winding number?
Yes, you could say that.
Yeah.
And you not only reconstruct the 0 level set, you reconstruct any level set also.
Thanks.
Thanks for the talk. I had a question about this hinge loss. So what goes wrong if it's not there? And is it like mathematically necessary if you were optimizing over the whole space of one Lipschitz functions? Or is it somehow related to the particular architecture that you've chosen to optimize over?
No, it's not related to the architecture. It's the result I showed that this loss, minimal this loss approximates the Stein-Nielsen function is continuous when we consider all Lipschitz functions. So what we have to do is to define some Lipschitz architecture. Actually, we tried different ones than this one, the one proposed by Anil and colleagues also before that, if you know a bit about Lipschitz networks. We settled on this one because it's more efficient to train in terms of computation time. That's basically the idea. But it can work with other architecture that represent one Lipschitz functions. Does that answer?
I think that answers half of my question, but also, like, what's going on with the hinge loss? Why do you need it?
Why?
Yeah.
Because we realized, and this was already an observation in the work of Serrurier and colleagues, that if you only do the optimal transport part, you have something that is very not precise at the interface. You get something that is very blobby, and you are not able to capture the details. And this is why they added this hinge loss to really capture the surface, the interface.
Cool, thanks.
Okay, there are no more questions. Let's thank Guillaume once more.
Thank you.
Thanks for the presentation. As you can see in the title, today I'm going to present a method, an acceleration method for distance queries to triangle meshes. As you can see in the other talks, distance fields are important in many topics, and therefore computing these distance fields from triangle meshes, it's important. In this case, we can find many methods, one that are more approximated, like, for example, these very old distance transforms that basically, given a uniform grid, they propagate the distances to compute the distances in the whole grid. Okay? The problem with this method is that its resolution depends on the quality of the distance field calculated. Therefore, we have other methods that are designed for computing the exit distances. No? In this case, for example, if we don't want to deal with these resolutions, to fix these resolutions, or for example, if we really want to get the nearest triangle, therefore, these exit distances are a better option. In this case, for example, we can find volume hierarchies that basically, given the volume hierarchy and a point, this method search for the primitive that is the nearest possible to the query point. Also, if we are working with single distance fields, computing the sign in the triangle meshes, it's sometimes complicated. In the case of close orientable to manifold meshes, it's easy because we only need to get the nearest triangle, and when with that triangle, we can compute the sign. Because in this method, we are focused more in computing and accelerating the nearest triangle. We will assume that for computing single distance fields, we'll deal with this type of meshes. Otherwise, we will have to use other methods like winding numbers to determine this sign. Okay, in this case, our method tries to improve the distance queries of volume hierarchies, sacrificing other aspects like the memory consumption or the building time. Okay, the main idea is we discretize the space in an octree, and each leaf contains the triangles that are influencing the distance field inside the node. And then when we want to do a query, we only check where the point, in which node the point belongs, and then iterate all the list of influencing triangles to compute the distance, basically. Therefore, in volume hierarchies, for each distance query, we need to iterate this tree until being sure that we get the nearest triangle possible. And in our case, we already have the list of segments that are possible in that part of the region. Okay, therefore, given a node C, for example, a segment that is influencing the distance field, it's a segment that at least at one point of the node is the nearest one. No? That we can rephrase this as that the segment that is influencing the node, its Voronoi region intersects with it. The problem is that computing a Voronoi region of a 3D mesh, it can be expensive. Therefore, we propose another method. In this case, we find a new region that we have invented. The name is not very good, region R, that basically what we do is we search this type of regions that fulfill the following property. Basically, given the region R of a node and a segment, if another segment doesn't intersect this region, then we guarantee that it doesn't affect the distance field of the node, and therefore we can discard it. Using these regions R, we construct our structure. Basically, we start with a big node that contains the space that we want to discretize, and then we start subdividing it. At each step, given the parent node and the list of its influencing triangles, we compute the influencing triangles of the child nodes. Okay, basically we get the parent list and discard all the triangles that we found that are not useful anymore. Okay, also important thing that I forgot to say is that in the whole presentation you will see that I talk about triangles, but in the pictures we have segments. Okay, the thing is that I will be always showing the 2D case because it's easy to understand. And finally, as you will see, it can be easily extrapolated to the 3D case where we have triangles. Okay. Okay. Now we have this how we construct this structure. and this region R. Let's define what is this region R. In this case, we can define the optimal region R, that will be the one that discards as much triangles as possible, as simply as the set of points that are near the node than, for example, in this case, the segment 1. No? Therefore, we can also define this as the union of all the spheres centered inside the node with a distance equal to the segment 1. Very easy. Also, what we can do is to do the intersection of the regions for each segment and get and accumulate all of the regions. That will be the same as getting the radius directly from all the segments. Sorry. The problem is that this optimal region, first, it's difficult to compute, and also it's difficult to do the intersection test between our segment and this region. Therefore, we try to find some superset of this optimal region that is good enough to discard triangles, but at the same time doesn't require a lot of computation time. The first superset that we can come up with is this one, that basically if we are doing this union of all the spheres. No? Therefore, if we fix the radius, we make the biggest radius possible, then we have this very homogeneous set that it's easy to test if a new segment is intersecting or not. Also, we can accumulate all these sets from each segment using only the minimum of these maximum distances. Okay, the problem about this, as you can see here, is that it's a very rough approximation of the optimal region. Therefore, this also affects the number of triangles that we select. Here in the right image, we have a yellow node, and in blue are the triangles that were selected using this method. In red, we have a try of simulating the triangles that will be selected using the optimal region. Basically, what we do is we sample points inside the node and print in red the triangles that we found that are near the samples. Okay? It's only to get an estimation of what will be the optimal selection. Therefore, we need another approach because we are selecting too much triangles and therefore our method will not work. In this case, if we recap a little bit with the definition of the optimal region, now we have this sphere that we make the union of all the spheres centered at the node and with a radius equal to the distance to the segment. Therefore, we can simplify a little bit this, estimating this radius using the interpolated distance in the corners of the node. Okay, in the paper, I will not prove it here because it's a little, we don't have time, but basically what we prove is that this is always a superset of the optimal if the primitive, that in the case is a segment, but it could be any convex polygon. Okay, any convex polygon will fulfill this property. Here, as you can see, this new region, it's more approximates better the optimal region, and as you can see in the right image, we are able to select less triangles. Okay. The problem here is that do this accumulate these regions for each segment, it's very difficult because we have to compute these intersections between these regions. Therefore, we define an heuristic. Wait, sorry. In this case, first we assign to each corner the region R of its nearest segment. Okay, and then when we have these regions assigned, given a new segment that we want to test if we can discard it or not, we basically share each n nearest nodes and test the region with it. Here we have an example where we have segment 4, in the case we are using the heuristic 2 corners, therefore we search the 2 nearest corners, and then looking at the example, we will test the intersection between the region S4 and the region RS3 and RS1. If any of these 2 regions doesn't intersect with a segment, we can discard the segment, okay? Here you have some results, building times using these different heuristics. As you can see, obviously, when we decrease the number of corners, we improve the building time. And also, we try another version that is using the centroid that here you have in the bottom one. That basically, instead of searching the nearest corners of the segment, we search the nearest corners to the centroid of the segment or the triangle. And we are able to reduce a little bit the computation time. Here we have an example of a plot of the percentage of triangles selected with taking as a baseline our method that checks the 8 corners. As you can see, as we decrease the number of corners, we are able to decrease the number of selected triangles. But every time that we add a new corner, this reduction is smaller. Therefore, we finally decide to use this the 2-corner strategy. And also, as you can see, between the strategy, the normal strategy, and using the centroid, there is no much difference in selection. Therefore, we decided to use that strategy. Okay, now we have a little bit the big picture. Basically, what we do now, we construct this octree using these art regions that we have defined. The problem is that we need to do this intersection test between this region that we have defined and our segment. To do this, we use the Minkowski difference. Basically, we do the Minkowski difference between the region and the segment and test if the origin belongs to this Minkowski difference. To do this test, we tried 2 solvers, the JJK and Frank Wolf, with some improvements specific for our problem. The good thing about JJK and Frank Wolf is that they only need the support function of the Minkowski difference. A support function basically is a function that for any direction, it returns the point that is farther away in the set. Therefore, this is a very nice property of the Minkowski difference that says that the Minkowski difference is equal to the Minkowski difference of one set minus the Minkowski difference of the other set in the other direction. Therefore, we only need to define the support function of the 2 parts that we want to test, if they intersect the segment and this region that I have defined as R by interpolation. The segment is very easy. We only need to test which of the vertices of the segment or the triangle are the farthest ones. In the other case, this new region we have is a little bit more complicated. Basically, here we have this region that we defined before that basically we did the radius of the spheres centered inside the node are equal to the interpolation of the distances in the corners. And basically, because we are using the properties of trilinear interpolation, we can guarantee that the support point will always belong to the support point of one of the spheres at the corners. Therefore, to compute the final super point, we only need to evaluate the super point in each of the 4 spheres and get the farthest one. Now we have some results. Here we have a comparison between the JJK and Frank Wolf and the number of iterations that they need to converge. As you can see, with Frank Wolf and the optimizations that we did, we're able to discard that to get a final decision with a few iterations in most of the cases. Here we have an example of a slice of this octree structure. We have different colors indicate the number of triangles selected. As you can see, as you can imagine, in the medial axis, this number of triangles increases a lot. Therefore, we will need even more subdivision. In this case, we are seeing an octree of depth 6. Probably we usually use depth 9 to get a good number of triangles. Here we have some comparison between our method and the volume hierarchies of Seagull and implementation of sphere volume hierarchies. As you can see, we are able to decrease a lot the query times. But this, as I said before, it comes with a consequence. That the building times are much bigger than the volume hierarchies, as it's obvious because we are discretizing the space and we need to do a lot more work. And at the same time, the memory consumption, because we have this octree that subdivides the space, we're also getting much worse memory consumption. Finally, here you have an interesting plot where we see the speedups that we get at different distances to the surface. As you can see, volume hierarchies are more efficient near the surface because basically they don't have to iterate the tree that much. And in our case, when we get further, we don't have this loss of performance. As a conclusion, we defined these new regions to test if which are the triangles that are affecting the distance field in the node, and we get fast query times, but at the same time we are sacrificing memory and the building time. As a future work, it will be good to test some compression methods to be able to compress this octree and reduce the memory consumption, and also try to know new strategies to combine these regions to be able to get closer to this optimal region that I talked about before. And that's all. Thank you for listening. And also, you can find, if you are interested in testing the library, you can find it in GitHub as SDFlib, and we also have a method for approximated distance fields. Thank you very much.
Thank you. Again, we have time for questions. If you have a question, please. There is the obvious question coming from Seagull. So while the microphone is arriving, I'm asking another question. So how you said it applies to convex polygons as primitives?
Yes, even the node could be.
That's not the question. So the question is, what are the restrictions on the cells? So now you presented it for octrees, where your cells are boxes, right? But I might want to use a different spatial hierarchy that doesn't generate boxes. Now, what are the restrictions on the cells for which you collect these lists?
Okay, sorry for interrupting first. And then, yes, basically, also for the nodes, we can use any type of convex polygon. Therefore, we can use any type of convex polygon for the segments, let's say, and also for the influencing part that we want to test.
But then maybe as a follow-up, your speed depends on the number of corners of the...
Yes, also this will be a problem in the... It's complicated.
Yeah, my question was in big O terms, so what is the memory consumption?
In big terms?
In big O, so it's
well, we have
cube of something, square of something?
More here. I mean, it's... it's getting, it's more or less 100 times worse. No, 100, yes, 10 times worse, sorry.
Asymptotically, how does it scale with
okay. Yeah, I think that it doesn't depend that much in, well, it depends in two factors, no? The number of triangles, obviously, and also the space that you want to discretize. Obviously, when you increase this volume, the bounding box, the nodes that are far will converge very fast. But yeah, you have to store all of these list of triangles for each node that are getting the required memory.
Thank you.
Thank you. Yeah, very nice method, thanks. Yeah, so your runtimes are really, really nice. So I think this is a really cool method. Just like the memory consumption is something that would concern me. And I'm wondering, so like you're using an octree, right? So you could limit the depth of the octree to avoid such a large memory overhead, I guess. Do you have any insight on how much performance this costs?
Yeah, the problem is that if you like limit number of the depth of the octree, then you are getting nodes that are not reaching this maximum number of triangles allowed that we are fulfilling. Therefore, then you are sacrificing query time also. Therefore, there's a trade-off between these two.
Do you have any insight? So when I see that, my first guess would be that the best thing would be to take a trade-off and say you go to, I don't know, level 5, 6, 7 or whatever in the octree, and then you do a BVH inside the octree. I don't know, is this something reasonable or?
It could be, right now I'm not sure.
Okay, that's fine, thanks.
Let me ask one. Any extension towards dynamic shapes? I mean, that's always the pain.
Yeah, that's the question. It's difficult to say because we are, as you see, the building times are huge. Therefore, doing this dynamically, it will be a difficult approach.
Let's thank the speaker once more.
Thanks, Marc, for the introduction. Thank you all for coming. Let A be this green flying animal who faces a pink boxing T-Rex. The Pompeiu-Hausdorff distance from A to B is the maximum distance from all points on A to the set B. Any ideas of what is the Pompeiu-Hausdorff distance in this case? Well, I mean visually, right? Not the number. The maximum distance from A to B. It's this distance from the tip of the wing to the mouth of the T-Rex. You possibly, as Marc said, know this as the Hausdorff distance from A to B, but it was actually proposed originally by a Romanian mathematician called Pompeiu, and then some years later generalized by Hausdorff. Throughout this presentation, we will assume that both and A are represented as triangle subs. And this gives us the possibility of dealing with objects with imperfections, such as self-intersections, non-manifoldness, etc. The Pompeiu-Hausdorff distance has many applications in computer graphics. For example, consider this mesh A with a lot of thin triangles that is remeshed into a higher quality B, higher quality mesh B. For the remeshing to be successful, it is expected that A and B are similar. This can be checked by verifying if the Pompeiu-Hausdorff distance is close to 0. Now, if we overlay both meshes, we can see that it's much more difficult to determine what is the maximum distance from A to B in this case. In this example, the Pompeiu-Hausdorff distance is approximately 0.09% of the length of the diagonal of the bounding box of the scene. Other applications include decimation, fabrication-driven approximation, and envelope containment check. For most of these applications, a small value of H is desired. The first approaches to this problem used a set of samples P, here illustrated by the black points, to approximate the Pompeiu-Hausdorff distance from A to B. The approximation for H was defined as the maximum distance from the samples to B, in this case, the bold dashed line. This is actually a lower bound for the Pompeiu-Hausdorff distance, since the maximum over a subset of A cannot be greater than the maximum over A. The methods used many more samples than in this illustration and benefited from acceleration structures to calculate point-to-surface distances, making the calculation of this approximation very fast. On the negative side, they could not estimate how close this approximation was to the actual value of H. To overcome this problem, more recent methods focused on calculating lower and upper bounds for the distance by using a global optimization framework called branch and bound. I'll illustrate all the steps of this methodology for this example, since our method is based on it as well. Notice that the maximizer for the distance in this case is the yellow point P star, and it is not any of the vertices of A. The first step calculates the distance from each vertex of A to B and defines the maximum among them as the initial lower bound L equal to 1.9 in this example. Then, for each triangle T from A, an upper bound U for the distance is calculated. This upper bound function is such that the distance from any point on T on the triangle to B does not exceed it. I'm going to be more precise about and define upper bound functions in a minute, but let's suppose for these illustrations that the upper bounds are 1.6, 2.2, 2.3, 2.2, and 1.6. Then the next step discards triangles for which the upper bound is smaller than the current lower bound. In this case, the wing triangles in this example. Indeed, since the maximum distance on the whole A is greater or equal to 1.9, and it does not exceed 1.6 on these triangles, the maximizer cannot belong to these triangles. The other three triangles from A proceed to the next steps. At this point, the global upper bound for the distance from A to B is defined as the maximum of the upper bounds, in this case 2.3. During all steps, the Pompeiu-Hausdorff distance h belongs to the interval from the lower bound to the upper bound. And the goal is to update these values to shrink this interval to some given tolerance. We keep performing steps of subdivision and bound calculations while lower and upper bound are not closer than a user-prescribed tolerance. The division by dA, the length of the diagonal of the bounding box of A, ensures that the scale of the problem is taken into account. The surviving triangles are subdivided using midpoint subdivision, leading to more vertices and more triangles. The distances from the new points to B are calculated, and the lower bound is updated, in this case, to 2.0. Then upper bounds for each new triangles are calculated. Triangles with upper bound smaller than the lower bound are discarded. The others proceed, and the maximum upper bound is also updated. This process continues while the prescribed tolerance is not satisfied. More steps are taken until the bounds are closer than epsilon. The maximizer of the distance to B belongs to one of the remaining triangles. The outputs for this methodology are the final lower bound and final upper bound for the Pompeiu-Hausdorff distance. A typical value of epsilon used by us and the previous method is 10 to the minus 8. This figure shows the basic scheme that previous methods adopted to process each triangle. Triangles that are not discarded are pushed into a priority queue that contains the upper bounds and the triangles in upper bound ascending order. The key for the success of this methodology is the choice of the upper bound function. Since the smaller it is, the higher is the chance to reject triangles. Each of these previous methods proposed their own upper bound function to deal with the problem. Since upper bound evaluation is performed usually thousands or millions of times, a bound with a computational simple formula and fast evaluation is desired. Unfortunately, bounds with simple formulas tend to reject less triangles and lead to more upper bound calculations and higher memory consumption. On the other hand, tighter and more complicated bounds make individual upper bound evaluations too costly. We overcome this problem using a cascade of increasingly complex upper bounds. A simple bound for the distance is computed first, and the triangle is rejected immediately is immediately rejected if this bound is smaller than the running lower bound. Otherwise, a second bound is evaluated, and the triangle may be rejected based on this bound. 2 more bound calculations are performed if needed. If none of these bounds are capable to reject the triangle, the final upper bound is defined as the minimum, among the 4 bounds, and this minimum is used to push the triangle into the Q. By using a cascade of bounds, we avoid the conflict between speed and simplicity faced by the previous methods. Our method uses simple bounds when they are effective and more complex ones only when they are necessary. Our approach is 16 times faster on average than the most recent branch and bound method on a benchmark with 10K mesh pairs. But before analyzing this plot, let's discuss each of the upper bounds we use. When the exact Pompeiu-Hausdorff distance from a triangle to B is possible, we first calculate this distance and use it as an upper bound. This is the case when all vertices of T project to the same triangle on B. The exact Pompeiu-Hausdorff distance H is given in this case by the maximum of the vertex distances. The rejection or push into the Q is decided based only on H, since this is the tightest possible upper bound. When the 3 vertices of T do not project to the same triangle on B, the first upper bound, U1, is calculated. All the bounds, including this first bound, are functions such that the distance from any point on T to B is less or equal than them. So it has to be from any point on T, so let P be a point on T. D of PB is the minimum distance from P to points on A. In this illustration, from P to Q. The distance to any other point on B is greater or equal to B. Let Q2 be the point on B closest to the vertex V2. D is less or equal to the distance from P to Q2. By the triangle inequality, the distance from P to Q2 is less or equal than the sum of the distance from P to V2 and from V2 to Q2. And the distance from P to V2 is less or equal than the longest edge emanating from V2. The same holds for the other vertices V1 and V3, so we define the first bound to be this formula with the minimum of these quantities that we analyze for V2. The second bound is the sum of the circumradius of T with the maximum vertex distance. For a proof of why this is an upper bound, please refer to the paper. These 2 first bounds are originally proposed by us and fulfill the goal of being simple to be the first ones calculated in our cascade of bounds. The next bound our method computes is the one proposed by Kang and colleagues in 2018. It has different formulas for when T projects to 2 or 3 triangles on B. So for more details, also please refer to our paper. The 3 previous bounds are too loose in situations like this. A very thin triangle T projects to two distant triangles S1 and S2 on B. Such a case happens when A has bridges and connections that disappear on B, are not present in B. We propose then a 4th bound to deal specifically, mainly with these situations. It is defined as the Pompeiu-Hausdorff distance from T to the vertex foot points Q1 and Q2. And this value can be calculated exactly by intersecting T with the plane that bisects Q1 and Q2. the maximizer of the distance from D to the points Q1 and Q2 is either the distance from the vertices of T or the distance from the edge plane intersection points. This example shows the importance of using more than one upper bound to reject triangles, which was the strategy used by previous methods. Let A be this triangle soup that is decimated into B with half the number of triangles. We show with different colors which bound was used to reject each triangle or subtriangle from A. We can see that all of them are used, and the fourth bound, the yellow one, is mostly used to process very thin triangles where the maximizer belongs to. We implemented our method in C++. The input triangle subs are represented as matrices in the VF format. The other inputs are the tolerance epsilon, which is usually taken as 10 to the minus 8, and a factor m that defines the maximum number of triangles to be processed, m times the number of triangles of A. The outputs are the final lower bound and upper bound. All calculations are performed using double precision floating point arithmetic. We used libIGL, Siegel, and Eigen to process geometric objects, matrices, and vectors. And specifically, we use libIGL's AABB3 for fast point-to-surface distance calculations. We now discuss the performance of our method. First, we show that using the bounds U1, U2, U3, and U4 in this order makes our method faster than any other order. For this experiment, a data set with 10,000 pairs of triangle soups was used, where A are soups from the data set Thingy10K, and B are the surface meshes obtained extracting the boundary of Tetwayo tetrahedralizations. We tested all possible orderings using only one bound, 2 bounds, 3 or 4 bounds, a total of 64 combinations. For each pair of meshes, we attributed to the bound orderings that were the fastest or less than 5% slower than the fastest a shared win. Here are the percentage of shared wins for some of the bound orderings. The ordering U1, U2, U3, U4, 1, 2, 3, 4, presented during this presentation, is the fastest with similar orderings close to it. We also performed comparisons to previous methods using the benchmark proposed by the authors of the previous methods. So here we can see the pair of meshes used by Kang and colleagues in 2018. We can see here that always A and B overlap a lot, right? And it's, again, a case of close to 0 Pompeiu-Hausdorff. These cases are close to 0. This table shows the average time of 100 runs of each method for using the 4 pairs. This comparison includes also the most recent method by Zhang and colleagues. And we can see that our method is the fastest for all pairs, especially the Ramesses pair that has millions of triangles. We provide a lot of additional details about this on this benchmark in our supplemental material. We also tested our method on the data set proposed by Zhang and colleagues in 2022. A are triangles from Thingy10K, and B are their decimations with half the number of triangles. So again, a lot of overlap between A and B, and we show here both of them for this case, and the Pompeiu-Hausdorff distance, not so close to 0 in this case, is indicated in yellow. So this is one of the pairs, right? And then this plot shows how faster our method is in comparison to their method. Each point corresponds to the speed up for a single pair of meshes A and B. We can see that most of the points are above the equal time dashed line, so our method is faster for most of the tests. We selected some outliers in this benchmark to analyze. So the first one is one of the highest points, so biggest speed up for our method. In this case, our method was 7,000 times faster for this pair that has a lot of intricate parts, internal parts. The yellow point on A is the maximizer of the distance to B. So where is my pointer? So it's here. And you can see that it belongs to a part that vanishes on B. And so this is the point on A, and the closest point on B is this, and the Pompeiu-Hausdorff distance is this, from A to B, is this segment. In this example, our method was 6,000 times faster, and this corresponds to the lowest point on the plot, a pair for which our method is 20 times lower than the method of Zhang and colleagues. As you can see, this pair is very simple, and actually both methods took less than 1 millisecond to compute this distance for this pair. The almost 10K tests from the previous benchmark revealed some limitations of our method that happen very rarely. For one pair, the inexact double precision computations led to an upper bound that is smaller than the lower bound for the triangle that contains the maximizer, mistakenly rejected it at some point and leading to an empty Q also at some point. Implementing our method with exact computations would solve this problem, but also make the method slower. In the previous benchmark, we gave 3 minutes for each method to return lower bound and upper bound. Our method took longer than that for only one pair, and the method of Zhang and colleagues took longer for 38 pairs. So, but if we give our method a higher tolerance of 10 to the minus 6, it returns L and U in 2 minutes. And in this case, the lower bound is the smallest for all the 10K pairs, revealing that this case is the closest to 0 Pompeiu-Hausdorff distance, and naturally demands more subdivisions and bound computations. So in this work, we focused on approximating the Pompeiu-Hausdorff distance from A to B. Some applications may need the two-sided symmetric version of the distance that is the maximum of the distance from A to B and from B to A. Running our method twice will result in approximation for this two-sided distance, but we think an interesting direction for future work would be to have a fast way to safely determine which of the two distances is the smallest, and then running our method only once. So we presented an accurate and fast method to compute the Pompeiu-Hausdorff distance from one triangle soup to another. It is accurate because it returns lower and upper bounds up to a given tolerance, and it is fast because it is faster than any other accurate method. We made publicly available our C++ implementation on GitHub, and we'll be glad to provide you with any support you may need. Thank you very much for your attention.
Thank you for the presentation. We have time for questions.
Thanks for your presentation. You mentioned that different bounds work better for different triangles. And I was wondering if you quantified or experimented with dynamic ordering of the bounds based on the triangles themselves, if that had any improvement?
No, we haven't tested that. We basically tested all the orderings to use only one. So this could be interesting, but the decision on what ordering to make could take some time, right? And then we may misfire what. So deciding if that was possible has to be a really fast procedure, right? So that's why we're using the one single best ordering for all triangles.
Cool, thanks.
Thank you.
Questions? I have one in the meantime. Sorry. I still have one in the meantime.
Okay, why the microphone?
Misha can wait. So
the microphone.
the microphone is.
Oh,
you
sorry,
have one. Go ahead. Sorry.
I didn't know that. Yeah.
I might have missed this. I apologize. You're doing 1 to 4 subdivision on the remaining triangles. That would require that no more than a quarter of the triangles get marked as requiring subdivision. Otherwise, you have more triangles, not less. Are there guarantees that you have sort of the geometric progression going in the right way?
No, this guarantees, you mean like that the bounds always decrease, for example?
No, that the number of triangles that don't satisfy the bounds go down by at least a factor of
No,
4.
but they may increase during the iterations, right?
Yeah.
They may increase, yeah.
They may increase. And so do you know that this has to converge? Or can you actually end up refining and refining it? Well, I guess you have...
Yeah, the most difficult pair here was a situation, was a situation like this. That it was taking so long because there were many subdivisions that have to be done. With the standard threshold 10 to the minus 8 took 7 minutes. So it finishes eventually, and finishes for the 10,000 pairs as well. But we didn't analyze like a theoretical analysis, right? What we have is practical results. It works very well in practice, but this analysis for sure would be very, very interesting.
I think it breaks easily. Just take a point inside the sphere.
Take a point inside the sphere.
Compute the distance from the center of a sphere to a tessellated sphere.
Mm-hmm.
This might just keep on tessellating forever.
I see, yeah. Yeah, it will never improve, right? Yeah, so, yeah, possibly, there are cases that it will take forever, yeah. Thank you, Mark.
Yes, yeah.
Have you tried to modify the policy for the subdivision? Or
to modify what, sorry?
The policy that you're using for
Right, yeah,
subdivision?
I have tried that with a subdivision called Voronoi subdivision that basically intersects when in a situation like this, for example, it's going to intersect the triangle T with the bisector of these two triangles, which is going to be a plane. Sorry, the bisector of the planes that support the two triangles. And then you have like not midpoints there in the subdivision. I tested with that and didn't get better results. So with the existing alternative, I didn't get better results. Of course, we could think of other possibilities.
I have another small question.
Sure.
So you need to compute here the circumcenter, right?
Yes, the circumradius, right?
So
there's a formula for that based on the vertices.
Yes. And is that sensitive, or do you need like exact computations, or is it something?
No, all computations, including the bound computations, we are not doing exactly. We're doing double precision, right? Mm. So this particular bound and also leads to this problem, this limitation that I mentioned in the end of mistakenly rejected some triangle that shouldn't. So the bound you asked about and the other bounds, for example, there's one on intersecting a triangle with edges. They're all double precision computations that may lead to problems. But our experiment was like a low tolerance, 10 to the minus 8, and we've experienced very few problems with that.
Just last question about, are you using ACMD computation or nothing like that here?
ACMD?
Like you are using this, you can pack numbers and apply multiple operations at once?
No, we're not using any strategy like this. Just regular double precision floating point computation. Thank you.
Okay, now I ask my question. So, do the results depend on the speed of the computation of the smallest distance?
Yes. Yes.
So did you experiment with that, and how does it
Yes.
change? You might have used the technique that was just presented.
Yes, yes. It can be directly plugged into our code. So, for example, the other two methods, the one from 2018 and the one from 2022, one of them used like a uniform grid, because the distances are always small, right, for near zero cases. And the other one was another AABB3. So in the supplemental material, we have the breakdowns of computations for the 4 pairs of the Kang method. And you can see that the pre-processing, which is the construction, first the construction, right, of the BVH is faster. And then like because it progresses better, our method is also using faster point-to-distance calculations. But if there is a better method, for sure it can be plugged in, but it has to return the distance from point to surface, the closest triangle, and the point on the triangle that's close. That's not difficult, but it has to have an interface that returns these outputs.
Any more questions? And let's thank Leonardo and all the speakers.
Thank you.